Hello and welcome back to Steam with Steve. Today I'll be focusing on our teacher friends by showing them how to apply digital fluencies when they create their own wind-powered sail car. The task was an open-ended problem-solving learning scenario where I designed, created, and evaluated a sail car. The car was timed over a 2-meter track and its velocity was compared to its mass. From Sparrow's research, I focused on the data and curiosity fluencies of the sail car. I was generally curious about how to collect data to help inform design decisions to improve the car's efficiency. Alexander's quote on digital fluencies resonated the most with me due to the amount of digital tools that were going to be used in this project. According to Chumbar and Chumbar, having an advanced understanding of creating spreadsheets is handy when inputting and analyzing data. I have a deep understanding from my software engineering background with Excel. An iPad and an iPhone was used to record the raw footage, with testing track being designed and printed from an industrial printer. Electronic scales were then used to weigh each iteration of the prototypes, with Adobe Premiere Pro used for the final edit, and to measure how fast the car was traveling frame by frame. In Year 12, I built a gravity car with the same principles as this project. The trick that our class worked out was to get the frame as light as possible and to transfer as much energy to the axle without the wheels slipping. I've also taught in the past how to build water towers and balsa bridges using triangulation to improve the frame strength. I also have advanced software skills from teaching and making YouTube tutorials. My initial research found the paddle pop car was the simplest but most effective design. I drew these initial sketches before construction and then purchased timber from Bunnings to glue together with a metal axle to be inserted into a PVC pipe. I've never created a sail car before and was very excited to see what could be done. The purpose of having the stronger frame though would allow for it to be tested multiple times without it breaking. I talked with Nathan McDonald, an industrial design teacher at school, and worked out that bracing needs to be higher to stabilize the structure, and instead of glue we used nails. 3 variables were changed in this experiment. The sail firstly was a large piece of cardboard attached by bending around the mast, secondly a flat sheet of cardboard, and thirdly a small flat sheet of cardboard. The fan speed had low, medium and high, and a variety of tyres were used with different properties such as grip, size and mass. The track was printed on vinyl to keep the surface constant. The checkpoints were placed at 50 centimeter intervals on the 2-meter course to get more insights of the car's change in velocity. An old industrial fan was used to generate the wind. Each prototype was trialled 20 times to gain better data insights. I was very curious to find out what variables had a direct impact on the model. By running through 27 different prototypes, I tested my curiosity by seeking the truth in the data with over 540 trials to improve the reliability of the findings. Using Adobe Premiere Pro, I was able to identify the exact time, including the frame number where the car hit each checkpoint. This data was then manually entered over another 8-hour time frame, and this time was significant, but the insights were also very important. The data from each experiment was then inserted into a summary table to show the max, min, and average times. Initially, only the velocity and weight was to be compared, but because of the multiple checkpoints, the potential to find average velocity and acceleration allowed for stronger insights. Trial 18 was by far the fastest velocity between checkpoint 3 and the end. It also had the best acceleration all the way to the end of the race. Power was useful for this experiment because it was a numeric representation of both the mass multiplied by the acceleration and the velocity. The power of trial 18 showed how much superior it was, and the similar data was found for the max and the min in these tables. Using the frame temp, I feel this project was relativistic with students needing some level of technology competence. But they didn't need to be experts when entering data. Students would not be directly instructed and would have some freedom when thinking about the concepts. Kelly and Knowles would be very proud of the STEM project due to the mass being the heavy lifter in the pulley system. The mass used helped collect data and create information to allow judgments to be made. But this would not be possible with another big cog in the pulley system being engineering. A lot of design principles and exploration and design concepts need to be done to complete these tasks. The other less impactful cog was science, due to the understanding principles such as velocity, acceleration, friction, and power. And the last cog was technology with recording of the data. To improve for the next iteration, I would make more checkpoints, upgrade the recording devices to capture more frames per second, and make sure the camera is focused before each recording. A device to measure the wind speed would also be useful. And then with funding, I would get multiple cameras at each checkpoint to improve the accuracy of the data, or at least put in laser sensors to check to be uploaded directly to a computer. A digital latch to release the car would also improve accuracy, and then SQL queries to investigate the data, or machine learning algorithms could provide deeper insights.